bachelor's and master's degrees in civil engineering from the University of Minnesota, before getting his PhD from the University of Illinois at Urbana-Champaign. And prior to arriving at CSU, he was the manager of the Nice Earthquake Laboratory, as well as a research scientist at Lehigh University. His research focuses on sustainable and resilient infrastructure in communities under different extreme events. And I'll let him take it from here, but thank you so much for being here.
Thank you so much for the kind invitation. Is everything okay? Okay, so thanks a lot for inviting me to kind of share some of the work we've been doing on wildfires, and excited to kind of show everybody some of the work we've been doing here in that domain. So I'm going to start with first acknowledging my postdoc, who's actually did his PhD on this topic, and Akshat Shulawat has been working on this for a while. He's done a great job. So I'll sort of provide some discussions for the outline of the presentation. I'll talk about motivation, vulnerability, assessment that we've developed, damage models, and then how do you actually do damage assessment? How do you communicate risk in a wildfire event? Because that's something I think is missing currently. And then finally, what does that mean in terms of impact on policies for managing wildfires? And then maybe couple of slides on discussions and future work. So wildfire is a big problem, obviously, and Boulder and Colorado in general is not a stranger to that. It's Marshall Fire is an obvious example of why we have major problems. And spending has been quite large on these wildfires. I hear a little bit of a echo, you guys hear. Yeah? Okay. Let's see. So managing wildfire has been a big issue that we haven't been able to resolve, and we're trying to understand what would be the best way, maybe refine or sharpen our calculations on managing wildfire risk. And to do that, we started to look at some of the possibilities of interventions. If you can look at interventions to try to prevent what you see here, essentially, on the left-hand side from happening, there's three different domains you can maybe play with. The first would be having fire-adapted communities. Maybe you'll have to have a resilient landscape because it can really uncouple landscape from community. They're kind of, even in some cases, they're intermixed. The communities are intermixed. We were not talking about just the wildland that interfaces with the community. But also you have to consider wildfire response, maybe firefighters and so on. So you can't uncouple them in a way. What we tried to focus on in this study is essentially looking at the top one, which is fire-adapted communities. And the reason why we want to look at this is because the increase in intensity and frequency and the tremendous amount of damage that we've seen so far obviously is pushing everybody to the edge. Every community has specific characteristics in terms of layout, geographical location, wind speed, wind direction, material types for the homes, and so on, that by intuition, it's probably obvious that a one-size-fits-all solution is not necessarily the right way to go. It will help, but not the right way to go. So in order for us to determine what would be the best solution or the best strategies, we need to have tools that allows us to understand how we can play with these strategies to understand how effective they are. And if you look in the literature, there's actually no tools whatsoever that would tell you if a building would survive a wildfire event or not. There are some tools that have been developed which take advantage of computational fluid dynamics, but these are computationally very expensive. So if you to run a couple homes and vegetation, one single vegetation, it might take a few months. So you cannot really use them for decision support models. And in order for us to be able to develop strategies, effective strategies, we have to develop them and communicate them in a risk way. So I have to tell homeowner or policymaker the probability of your home burning is, or surviving, hopefully, is X. And because the word probability is in my sentence, that makes the argument for probabilistic analysis, which means we have to run a lot of simulations, which means even if your CFD model can run at a community scale, still it's an issue because you need to run thousands of analysis in order for you to run probabilistic analysis. And so we started by looking at the vulnerability, and you can clearly see the vulnerability kind of divided into different stages that vary from ignition to propagation to ember attack to finally fire propagation in the community. And if I want to look at all these stages, which arguably are important for risk, one of the things that we don't know much about is essentially fire propagation in communities. So we started by looking at actually fire propagation in the wildland, and I'll explain why we did this. But essentially, we used a concept that's called cellular automata, taking advantage of, it's like a rule-based model or approach that allows you to determine the probability of one of these cells, which represent a wildland. The green represents maybe vegetation, the water is represented with the blue cells. And you can use this rules-based approach to determine the probability of one cell going from one condition to another. And these conditions could be represented with these different colors. For example, for the fire, where 3 implies the fire is at the highest intensity possible. And if you use this approach, which we were not the first to use cellular automata for fire propagation in the wildland, you can come up actually with very interesting models. And without digging too much, because that's not the focus of what I want to show you today, the cellular automata model allows us to actually consider different burning rate of vegetation. We also can capture the effect of wind speed and direction. We can actually consider the topography of the land and consider ember generation and flight patterns of the embers. And so you take a 3D map like what you see on the screen here, you can actually turn it into a 2D map that gives you the propagation in the wildland, and then you can even track the ember as it lands across your field. So this is a model that allows us to capture fire propagation in the wildland. And we've calibrated this model, and we've shown that we showed that it works pretty well. Now, these colors that I want to point out too, that you can see the yellow, the red, the black, and so on, is essentially the fire intensity that I showed you on the previous slides, right? The different colors. And this becomes important because we're going to use it later in my community model. This community model is established based on the concept of graph theory. We first argued that a community comprises of ignitable and non-ignitable objects. And then we can actually develop nodes or create nodes that represent the edges of a house or a home or a structure, and then connect these nodes in a way that allows us to model the interaction between the homes. So you can see this is actually Fort Collins, a piece of Fort Collins. And what you can see on the right-hand side here is actually the graph for 3 homes showing you how they're connected with the nodes. And it allows us, this graph theory approach allows us to actually model fire propagation within the community. So without going into super duper details, in a way, this kind of is described with the slide where it shows you the community and you have the vegetations and the buildings. You have to determine what are your ignitable objects. You can see that on the bottom left picture where we have the homes, and the vegetation has to be considered. And then this PTR that shows that is shown on the slide between the different objects is essentially the probability of fire transmitting from one node to another. And this fire transmission takes into account convection, radiation, and impulse spawning. So all these are included in these links. And the graph, again, for simplicity, you can envision it what you see on the top right here with these nodes and the links in between. So now the colors that I showed you earlier, where the fire is coming from the wildland and it's coming into your community, can be represented by this bunch of colors you can see at the edge of this box. And now envision that you have a bunch of nodes inside your community, and these nodes represent vegetations and buildings and so on. You can classify the nodes as boundary nodes. These are the red nodes. The boundary nodes because they're the closest to the wildland boundary, which is the small little colored cells at the edges. And then let's say the node in the middle, which is the blue node, is what I'm interested in terms of ignition, or in terms of probability of ignition. And between the red nodes and the blue nodes, there's a bunch of other nodes. It could be homes, it could be vegetations, it could be both, it could be something else, right? So essentially, we have to identify all nodes. We calculate the weights, which is the probability of the fire transmitting. But then we have to figure out what is the most probable path from one node to another, from one of the boundary nodes to the blue nodes, because there's so many different possible paths. We have to identify the most probable path. And then ultimately, we have to sum across all boundary nodes to get the total probability. And this is just a schematic that shows how it works. These are the different probabilities that I mentioned: the convection, radiation, spotting, and conduction. And conduction, in that sense, we say if a fire hits a house, therefore this house burns. We're not looking at how the fire travels inside a home, right? We assume it's gone. And just to reflect on some of these without going into the mathematical models, but to show you what this is a function of. So you look at the convection model. The convection, which is the fire front moving towards the community, is a function of the distance between the nodes. And again, these nodes could be structures or vegetations or both. Effective wind direction is included, flame height and flame angle. The Ember model takes into account accessibility probability, so the probability of your ember accessing the other vegetation or other structure. We have to take the effect of wind direction into consideration, and also ember distribution, which is related to the volume of the node or the volume of the tree being burned, because the bigger the tree, the more ember will be generated, and the type of the tree, of course, matter. Distance between the different nodes and wind velocity. And the radiation model takes advantage of a very famous radiation flux model. It's called the Stefan-Boltzmann law. We just took it and applied it to a house-to-house ignition for radiation. So you can look at the Stefan-Boltzmann law and you look at the radiation flux from one surface to another to be a function of the area, the view factor, emissivity, and temperature. And this just shows you what it's a function of without going deep into details. But the nice thing about doing that, actually, interestingly, it allows you to look at how each surface from a home, from your house, might radiate heat on the other surface of the other home, which is pretty cool. And in the process of doing that, the inclination between these different homes is taken into account. And if you look at, for example, at the top left inclined surface, which is called the 3, that surface is receiving heat flux from actually 2 different surfaces from the bottom home. And mathematically, it's very convenient because when we do that, we can get the total flux on one surface, which is the big Q. And we can actually maybe even arrange that total flux in a matrix form, as you can see down there. And the also nice thing mathematically makes it convenient for calculations is if you actually take the transpose of this matrix, you get the amount of flux from the top building on the bottom one. So if you actually take the transpose of that, you get the opposite value, which is really cool. And so this is just to kind of show you a little bit of information on the model. One of the things that, of course, is really important to consider is vegetation. So we looked at wildland and urban vegetation. For vegetation around homes, we actually incorporated, for the wildland, we actually added more node to kind of give us the representation of wildland vegetation. But around the homes, we actually adjusted our PTRs, which is the probability of fire transferring from one node to another, to take into account the vegetation around homes. But for the wildland vegetation, which is also really important, there is a lot of data online, which is very good for us because you can go to these files and find the different vegetation types, flame length, flame bed, or bed depth, and fuel volume, and so on. And then you can actually establish a grid that has all the nodes of these vegetations with the specific characteristics for these vegetations. As I mentioned, the urban vegetation around communities or around buildings is essentially taken as an adjusted factor for the probability of fire transmitting between 2 different nodes. But it's also very important to consider. We have some ideas for how we might want to refine that in the future. Then we actually coined the term called relative vulnerability. One of the really interesting things to think about is that how a building in a community is actually vulnerable relative to other buildings in the community. And this is really important because it allows you to define which buildings are the most at risk and which buildings are not at risk. And also it allows you to identify which buildings matter the most for the risk of neighboring buildings and for the risk of the whole community as a whole, right? So that relative vulnerability term was actually very useful. Structure, obviously, with higher relative vulnerability are expected to have lower chance of survival and vice versa. So when we put it all together, skipping tons of details, we start to look at damage. And we did two things. Now, one of the things that are obvious is you want to actually look at one-to-one correlation. If I show you a fire somewhere and you know exactly which building was damaged, which one was not, you want to see the correlation. Did you actually match that or not? The other thing that is actually important to reflect on, and I'm going to start with the bottom one, is that in our model, the model calculates what we call relative vulnerability, right? And we put it in pins, like you can see 0.1 to 0.2, all the way to 0.8 to 0.9. So if the model tells me that this building in my model has a low vulnerability, low relative vulnerability, I would expect it to survive in reality, right? So if the model says the relative vulnerability is low, then it better had survived in reality. And the higher the relative vulnerability, according to my model, the less likelihood of survival, right? Technically. So if my model says this building has a very high relative vulnerability, if I go in the field, most likely I'll see it, right? Gone. Make sense? So what we did is that we looked at the values for each building that we have. So if we look at this pin 0.1 to 0.2, we see how many buildings fall within that pin within my model, and then we look at the real data, figure out did they survive or not. And if the ratio of that is 1, obviously you're an excellent match, right? And if it's not, then it's not an excellent match. Now, are we expected to get an excellent match of exactly which building survived versus not? In reality, no. I mean, it's one heck of a hard problem to solve. But the thing that the model should do at least is to actually have a monotonically decreasing curve like this, right? That the model should tell me it's doing something right when I get a monotonically decreasing curve, implying that, yes, I am capturing the buildings that are likely to survive. Yeah? Okay, so that's a very important. The other thing is that you can actually plot some histograms that shows you for each relative vulnerability value or range, how many total buildings are in your model, how many destroyed, how many were not ignited, and so on. You can look at these different distributions, for example. So now, we ran this on the Camber fire to start with. This is the 2018 Camber fire. What you can see on the very far left is the observed damage from the Camber fire. What you can see on the right-hand side is the relative vulnerability from our model. And what's in the middle is us taking the relative vulnerability, which is that contour map, and turning that into 0, 1, meaning survived versus not survived. And when you look at the survived versus not survived from our calculated analysis, which is the middle picture versus observed reality, you'll see actually the match is really great. Sure, it's not excellent. We don't expect it to be excellent, but we're getting very good match in reality. And in this slide, we're not showing the vegetation nodes because it kind of makes it, then you cannot see anything. So what we're showing here is only the building nodes. But you can see, even without me turning anything to 0s and 1s, meaning damage or no damage, the pattern with the relative vulnerability calculations matches relatively well with the pattern of damaged structures. And then when we turned it to a 0 and 1, we managed to get a very good correlation, one-to-one correlation. The survival curve, again, is monotonically decreasing curve, and you can reflect on some of the distribution for every different vulnerability pin in terms of how many buildings in total you have, and of these total buildings, how many survived and how many did not survive. But getting an 85% match is actually wonderful. So we thought this was, okay, this is luck. We ran the first analysis on one of the fires called the Tops fire. And the Tops fire was almost 100% destruction everywhere. And the funny thing is that there were few buildings that survived, and we thought something is wrong because we actually captured that these would survive. So I told the student, something is not right because we cannot be that good. So we dumped the tops fire and we went into the camber fire. When we did the camber fire, I said, something's not right because it can't be that good. So we decided to do something else, and we did the glass fire. And it's not as great, but still getting a 64% match, capturing some of the blues matches almost exact with the blues and the reds with the reds. This looks great. And the monotonically decreasing survival curve is also something else we expected. So that actually worked quite well. And we did this finally on the Marshall fire, and we got 72% match. And you can see actually the blues and the reds for the left figure, top left and middle one match also relatively well, which is great. And since you guys are in Boulder, I just want to complain a little bit. Coming from CSU, here's my complaint of the day. We tried to get access to areas that were impacted for the purpose of trying to run some analysis and so on. We were told maybe not at this time. So we ran this analysis entirely with data we collected online. So it could have been better accuracy had we had better access or had some sort of access to better set of data than that we managed to produce ourselves. There was some really good data online. The county put together nice data on which buildings were damaged and the streets, and we used that, but it was difficult to get information on building material by just looking at Google Pictures. But nevertheless, this is 72% match is actually pretty decent. And if you actually zoom in on the Marshall fire a little bit, because that's an interesting case, you can see these, you saw the top pictures from the previous slides, but the bottom two rows is essentially observed damage, zooming on specific regions within the community, and the predicted or the calculated, which is from our model. And sure, it's not 100% perfect match, but we are identifying the most critical areas within the community. I mean, it's quite obvious that the model is doing something that is actually working. So then, of course, you know, one of the things you would ask as a community leader is, how would you make use of this type of analysis or models? And first, before we kind of want to reflect on policies or reflect on decisions, it's important to make sure that homeowners or policymakers understand that this is one single simulation. Sure, it's probabilistic, but it's based on wind condition, wind direction, wind speed at a given day. Reality is, and ignition probability at a given day. The ignition in the Boulder fire, it's not, or the Marshall fire, is not 100% identified yet, but they have an idea it came from a shack somewhere, and right? Well, what's the probability of ignition at a given day? So if you want to communicate risk, you have to understand the ignition probability for your region. And this could be based on statistical models from data collected, right? People that go and maybe do grilling in somewhere in the forest in specific areas are more likely to ignite than other areas. And then the cellular automata model for fire ignition in the wildland is very important to tell you if that ignition that happens in the wildland will get to your community or not. And then the vulnerability model that we ran is also very important because it tells you which homes are more vulnerable. And if you do this type of analysis for every day of the month and for every month of the year, then you get a much better idea of how your risk is actually varying across the whole year. Now, I'm not sure what to do about this data because, you know, it's overwhelming, but you could take an average. You could look at the most important months of the year when you actually sources are down and so on. So the writing is a little small on this, but I'll just explain. So you look at ignition probability. We calculated ignition probability based on what's called danger maps you can find online. And we calculated that for every month of the year and for every day of the month. For the year 2007, 2012, and 2019. I believe we did 5 years, or 2017. So you have the ignition probability for every day of the month, for every month of the year. And we did that for the month of May until September. We didn't do it for the entire 12 years. But you can see how the ignition probability varies for every one of these years. And there's maybe some sort of patterns in specific years because it was harder than other years and so on, but you can see the variation in the ignition. The vulnerability that I showed you, the model that I showed you, depends on wind speed and wind direction. So we downloaded wind speed and direction from NOAA website, and that's the sustained wind. And we can run the model on these two communities that we've played with, which is the Steamboat and Jackson, Wyoming. And then we get a vulnerability every single day of the month and every month of the year for the 3 years. And then you put them on top of each other, you get a total risk. And you can see now how the risk changes every day of the month, every month of the year for the 3 years that we looked at from September or from May until September. And so a policymaker could look at this and say, oh, we need to do something about it, right? These are the days where the risk is the highest, and these are the days we have to be on alert. These are the days that we should prevent people from maybe doing camping or something, and we have to be careful. I mean, something like that could be done with this analysis. But there is a bigger picture when it comes to policy impact even, because I'm just giving you some sort of a sense of how you can use this type of analysis, but there is a bigger question to be answered here. What would be the policy impact, if you would? Now, if you look online, and again, agencies have done a great job in trying to reduce wildfire risk, but this image tells you the whole story. It says, wildfire is coming, are you ready? The way it's viewed here is that, are you as a homeowner ready? Not are we as a community already? And the importance of kind of conveying the message that this is a community effort, not an individual person effort, is because if there's, a community has 100 people and 3 of these or 10 of these did whatever they need to do, that might absolutely not move the needle whatsoever on lowering the risk, not even for themselves. It might lower the hair, but the probability of the homes igniting is still really high. All that money is nothing but wasted. So the fact that we're not enforcing wildfire mitigations at a community level is alarming, because you could, some people could do whatever they think they need to do, but the risk is really high because they haven't done anything, right? They haven't lowered the risk for their homes. They're getting hammered by embers. They're getting hammered by homes next to their homes. And at the same time, the nice thing about the model is that it shows you a good picture of the fact that you don't have to do this for every single home in the community. And that's the nice thing about it. Yes, we need to enforce, but we don't need to enforce it on every single person. Some homes are completely irrelevant as far as risk goes, right? Some are very critical. And I always make the argument, this is very similar to disease transmission, COVID-19. Some people are more vulnerable than others. Some people transmit the disease more than others, and therefore we need to really understand which homes are more critical, which homes transmit more, which homes receive more, in order for us to develop effective policies, right? If we have a lot of money that we don't know what to do with it, sure, we can tell everybody do whatever is needed that's gonna lower the risk. But in some cases then, if the whole community, every single person would do everything that they need to do, that also doesn't mean the risk is reduced quite a bit, and I'll show you why. And so we looked at 2 different things. We looked at passive and active fire mitigation. Mitigation that are called the passive is essentially applied to prevent ignition. So you see that home up there on the left is actually we're trying to prevent the fire from igniting that home. And passive is essentially applied to prevent spread. And so the model allows us to actually reflect on these different passive versus active fire mitigation scenarios. And so we did 2 things. We selected building nodes at random and specified a certain mitigation strength, meaning we're impacting the probability of PTR, these PTR values, to imply active versus passive fire mitigation strategies. And you can see this alpha term here that motivates the PTR and the beta term that motivates the PTR in order for us to get to influence the behavior through active and passive fire mitigation. And so now I show you what we did, for example, for the camp, the glass, and the Marshall Fire. So what you see on the screen here is different wind speeds on the x-axis, and on the y-axis, you see the building damage in terms of percentage. And the variation here, because we're not doing an optimization, we're actually selecting nodes at random, and we're saying, okay, we're gonna run the analysis a lot, 1,000 times, 1,000 iterations. And so that distribution, you see this thin lines that you see, vertical lines, it shows you the minimum and the maximum in terms of building damage, percent of building damage, when the percent of buildings that have fire mitigation, so 20%, 40%, 60%, and 80%. So that's interesting because it says that the mitigation strength obviously varies, but it doesn't matters. But the mitigation strength in terms of percent of building in which you apply mitigation to is actually irrelevant at low wind speed, right? At low wind speed, the variation between how many buildings I select mitigation is not that, it doesn't make a big difference. But when the wind speed becomes larger, it does make a difference at the percent of building in which you're applying mitigation strategies. And the fact, again, that you have this distribution with the mean and then max and min implies that it's very important which buildings get selected for fire mitigation, right? So when I do 20%, which is the red line, for example, on the Marshall Fire, there is a specific selection of buildings, even if I do the 20%, that will lower damage, percent of damage overall to the community. I shouldn't just pick any 20% and say, these will be mitigated. And if you really want to lower damage, I'll pick on the Marshall Fire again. If you really want to lower damage, then the 80%, for example, the percent of building in which they have mitigation should be about 80%. If you do 20%, it's a waste of money. 80%, you reduce damage in the whole community quite a bit, right? So don't make it volunteer effort for people to mitigate their homes. The other thing that is really interesting is for the active fire mitigation, you see similar trends, but for the Campo Fire, you saw that actually the percentage of buildings that are being mitigated becomes completely irrelevant in the Campo Fire. Right? So you're essentially wasting money. Sure, the wind speed matters again, but it's very obvious it's not making much difference, the percentage of buildings in which you apply the fire mitigation. And the implication for policies is that the impact of fire mitigation is different in all cases, as you saw, but the variation is more noticeable for active than passive fire. So we should focus more on active sprinklers, for example, right? Positioning firefighters in a better way. And then passive is more important. And then the wind speed clearly impacts the behavior. And the selection of buildings makes less of a difference because you saw the curves are really narrowly spaced at a low wind speed. But at a high wind speed, it's very critical which buildings we select. And a one-size-fits-all strategy is actually not working. And the model clearly and the results shows that a one-size-fits-all strategy is not the answer. This is obvious from the results so far. The model we developed, we came up with that term relative survivability for individual buildings to identify critical areas within a wildfire affected zone. We have another model that we can run to get the actual fire boundary if we want. The cases I showed, we already knew the boundary, so we didn't need to run that model to get the boundaries because we already knew the boundary of the fire. We just calculated which buildings will survive versus which building will not. But we can combine all of them to get the boundaries, even for a community that has never been impacted, to know the extent of the fire scar in the community. Predicting structural survivability is key for determining effective policies. I hope I made that clear. We can determine which building needs to be hardened to benefit the whole community. And risk varies by the day and the month. So it's really important to reflect on that and not just take a bad scenario and say, I'm going to actually try to develop mitigation strategies based on this one single bad answer, if you would. The model can be used to determine optimal firefighting strategies as well. And we're currently expanding the model so that we can actually propagate the fire over time. Because what I showed here, there was no time element in terms of the fire is propagating over time, and it takes 4 hours to get from point A to point B. But we are currently working on that piece. And with that, I want to thank you again for the kind invitation, and if there's any questions, thank you. I don't know if people can, yes.
Yeah, I think you can watch the chat too.
Okay, yeah.
But I have a few questions.
Yeah, yeah.
I'm Max Cook. I'm a second-year PhD student with Jennifer Walsh in our lab. My research is really focused on social ecological systems of wildfire, particularly around structure plots. So this was incredibly interesting. The work you're doing is really important.
Thank you.
You're pulling together all these different data sets that are commonly used in fire simulation modeling, but in the context of sort of the built environment. So I guess some of my questions relate to limitations or gaps in the data that you came across as you work through this project. And in particular, where and how did you incorporate building materials and that type of data? It seems to be fairly limited.
Yeah, that's a great question. So the data and the data quality is really important because it's not only for the buildings, but also for the wind and so on. For the building specifically, since you asked about that, for the Camber fire, we used data from the Cal fire. They had a very nice, rich data set that explained material type and properties for every single building in Paradise. So that made our life very easy. Actually, we did that for the Camber fire and for the Glass fire. They had this data set. It's obviously easy to produce because they produced it. And what we wanted to do for the Marshall fire, before we got our own data, we wanted to drive a car around that has a camera on it. It would just take pictures of everything, and we post-process it using a machine learning algorithm, and it tells us all the properties that we need. But in the absence of that, we ended up going to Google, and we're lucky enough because it's only 2,000 or so buildings, so it's not 14,000 like the Marshall fire, the Camber fire. So we zoomed in on every single building, more or less. I mean, I told the student, you don't have to look at every single one. If you divide it in grids and take one out of every 25 or something, that's sufficient representation. And this is not the most accurate, but it seemed to give us really good results in general. 72% is not bad. The other thing that is important for the model to kind of even refine that, and I honestly don't know how much more kind of refinement we can do, because the results right now, in my opinion, is sufficient for policies, right? So if I get the Camber fire, instead of 85%, I get it to 93%. Is it going to make a difference in the policy at the end? I don't think so. But I could be wrong, but I don't think so. But the other data that would be important is the vegetations around the homes. And we did that also with for the Camber fire, we had data. And as well for the Glass, but for the Marshall fire, we actually zoomed in and we had to look at it, and we generalized for the whole community, and we didn't have a specific value for every single home. And maybe that's why we got 72% for the Marshall fire. I don't know. The wind field was also complicated for the Marshall fire. It wasn't straight wind. It went and it looped around. But there's obviously the possibility of potentially taking the Google images automatically using, again, a machine learning algorithm that is trained on images, and it will tell you what every single parcel has in terms of the homes around it, in terms of the vegetations around it exactly. And then if we have that, then we'll have a better way to modify this PTR values for the links for the graph model.
Yeah, that's really interesting. Thank you. I see remote sensing as possibly being an avenue to expand
exactly
into a larger region where you're running this probabilistic across the country.
Right, exactly. It needs to be automated, and some people spotted the model after it was published a couple of months ago. I mean, we started to publish it 2018, but they had the exact same comment. Some policy people, they said, in order to run this across a very large scale and do it for tons of communities, it has to be automated, which I totally agree with. Yes, please.
Yeah, I'm curious, I guess the way you were talking, I'm guessing that you have an answer for this question, but it sounded like the relative vulnerability is very important to validate the model, but you were also talking about the importance of particular structures compared to others. And to compare conditions to other buildings damage.
Right.
You have some kind of a metric that you have.
Yeah. So the we had to validate it first so people can take us seriously in terms of when we say, here are some recommendations for policies. But and I apologize if I didn't make this too clear, but this is exactly these. You can see the spread even more. This thin line that you see here showing the minimum and the max. So essentially, at every single wind speed, we run tons of analysis for a specific mitigation strength. Let's say we selected 20% of the homes will be mitigated. That's our decision. This shows that it doesn't matter which 20% you select, because you can select a certain 20%, and the percent of building damage would drop to, let's say, 11, 12 versus all the way to 15. It depends on which 20 you select. So this clearly shows, and this is the case for pretty much every single analysis. It clearly shows that there is an optimal selection that would actually allow you to lower, if all you can afford is 20% of the buildings, right? Then you have to really select them in a proper way to minimize the damage. Otherwise, if you don't, you can get higher damage value. So these lines show that. Yeah.
Quick follow-up on that. Would you be able to track that for your model?
Yeah. We just didn't. I mean, which building? Yeah, you can. Easily. You can. Every single analysis you can run, and you can keep an image of the nodes, right, that you've applied to. Yeah, you can easily do that.
I think that would also be curious if there are qualities of buildings that can predict that about the drought. I mean, it doesn't sound like this is very expensive, other than that you have to get all of the data.
Right.
I'd be curious, like, what makes it so nice.
Yeah. So the proximity of the buildings to each other, the wind speed and the wind direction in relation to where you are relative to your neighbor, the amount of vegetations around the homes, including obviously the wildland vegetation, because in the case of for example, in the campfire, there was not much wildland vegetation, but campfire and glass fire, there was a lot of wildland vegetation. So there's different parameters, but it's actually, it's somewhat for someone who's been working in this area for, firefighters and fire chiefs, been doing this for a while, because I've spoken with some of them, they can kind of have a sense of what to expect in a way, but they cannot really tell you exactly what's going to happen unless you're on a model like this. And we were talking to two fire chiefs that, starting to try to collaborate with them. They asked us to run some analysis. They said, we have an idea of what would happen. They just wanted to see if the model will do what they think it should do. And the results came out in a way that matches their intuition, but they can never tell you, yes, this building is going to ignite versus that one is not. In general, they said, yeah, this makes sense to us. This is what we would have expected, but they cannot, right? They cannot make the identification like this model.
But isn't that like almost literally one of these annual time thinking back? So the thinking back that works better here.
Yeah, exactly. And developing a model like this, I always argue, do I want to rely 100% on this? I want to rely on it with the experience of a firefighter as well, right? Because they have tremendous experience to reflect upon and say, yeah, I mean, based on the model results and based on what we know, I think the final answer should be this. So, and you've alluded to the question of how long does it take to run? 5 seconds. I mean, it's amazingly fast. Once you build it, we haven't automated the building process yet. But to build a model depends now on where we get the data and how long it's going to take us. But if we automate the building the model, it would probably take 10 minutes and run it 5 seconds, and that's it, which is very convenient.
Oh, I do have another one. There's a comment in the chat. Thank you for the excellent presentation. I come from a hydrology background, and we use many similar techniques to assess relative vulnerability for water resources. So it's interesting to see these methods applied to forward.
Wonderful comment. Yeah. Thank you.
And then in that context too, I had a quick question. Fire models that are used in terms of wildland fire spread don't do well in urban settings.
Yeah.
And this is obviously the step in the direction towards incorporating urban And so have you looked at comparisons of sort of the graph theory fire spread models compared to things like FSIM or PlanMap or the commonly used fire models?
We haven't, because we knew from the literature that they're not, I mean, they provide nice insight, but they're not perhaps the best suited for the problem. We haven't compared, we just compared what we got out of, to reality, and that was our measure. But I will argue that if, the first slide I showed, where if you want to establish effective policy, we have to look at the community, but we also have to look at the wildland. Because it's not just which homes need to be protected, it's what's the most optimal way to do it. You have to protect certain homes, but you also have to have a certain level of fuel that, so fuel reduction has to be optimized with mitigation strategies within home. And you can obviously optimize fuel reduction for reducing risk in general, but also you have to keep in mind other things related to ecological health of the forest, other parameters. So it could, become a multi-fold problem in terms of how do you come up with the most optimal strategy. But you have to look at community level and wildland as well, combined. Yes.
Okay, thank you very much for the presentation. I really like it. Yeah, very interested in models. So my first question is related to the spatial resolution of the analysis, because, for example, I saw that you use nodes, like you probably read your data, spatial data. I don't know if you read to. And I'd like to understand what resolution you work with, because, for example, the wind data probably has a coarser resolution, and then you have a building in a finer resolution.
Right.
And what's the resolution of the model?
Yeah, that's great. So the resolution for so we did this for every single analysis, try to speed it up a little bit. But the resolution for the model, as far as the building nodes, is 1-to-1. So for example, the campfire, we had 14,000 buildings. The model has all 14,000 nodes of these buildings. The vegetation within the nodes, you can actually go down to a certain level of resolution that becomes your minimum threshold versus a higher level of resolution that becomes maybe a higher threshold. So we looked at different resolutions for the wildland vegetation, and what we did to actually make the process faster, for example, so the Marshall Fire had no wildland nodes inside the community. It was what we call urban vegetation. But the campfire had vegetation, and what we did, we looked at a grid of 10 meter by 10 meter. I use the meter because I'm most used to that. And then we looked at the distribution of the vegetation within 10 meter by 10 meter, and then that's the distribution that we used in our model. So for example, you can go in that 10 meter by 10 meter and see how many vegetation nodes that you have within the zone, how many vegetation nodes you have within that 10 meter by 10 meter, and so on. And these are the nodes that you would put in your model. In some cases, we automated that piece of it. But in some cases, if you might end up with a lot of vegetation and a lot of nodes next to each other, because there's tons of trees. And the automated process can capture every single node, but it makes the computational analysis more extensive. Maybe it will run in 10 minutes, perhaps, right? So you can even take, let's say, within 10 meters and 10 meters, if you have hypothetically 50 trees, you can take these 50 trees and collapse them to 20 trees that are, that combine few of these nodes together. And that's what we did for the campfire. But for the Marshall Fire, we didn't have to do that. For the glass fire, we didn't have to do that either. Yeah. Yep.
It's just a note. We're working with the team here on developing a fine-grained surface urban fuel mass that's developed from the Zilla Z-Tracks database.
Oh, interesting.
And so I'd be interested to follow up with you.
Yeah,
if that's
really cool.
The course of resolution is a 250-meter resolution, but you get % of certain types of building material based on the Zilla data. So I'd be interested to follow up.
So the fuel is the building data, the building material data. Essentially, cool. Okay.
But there's a lot of talk around combining this 250-meter resolution and urban fuel mass with vegetative fuel and doing, looking at the combination of those urban fuels and vegetative fuels.
Right. Yeah, that sounds really interesting. Wonderful.
Can I ask you to give us like a recommendation of a landscape, like some way to mitigate or adaptation, like how we can have more adapted landscape?
Yeah, it's difficult to provide that in a general sense because every community will vary. But I would definitely argue that, I mean, some of these, I guess, I just want to see if there's any more comments. So some of these clearly suggest, and just take the campfire as an example. The campfire suggests there's an optimal value because you still have these thin lines that show you minimum and maximum. So you have to be very good at selecting which homes you want to optimize or you want to mitigate. But it really didn't make much difference whether you're mitigating at 80% of the home, mitigating 20% of the home, or somewhere between, because the percentage of buildings damaged is pretty much the same. Of course, the 80% is slightly better, but it's not substantially better. So one would have to know what the community looks like. One would have to know what wind speed you're interested in, and then determine the percent of mitigation that allows you to lower the impact to the most. So obviously, for example, in these particular two cases, Marshall Fire and Grass Fire, doing 80% mitigation obviously lowers the wind speed quite a bit. But if you come and say, my community is subjected to a wind, we know this. We know that the average sustained wind is 8 meters per second. Then for 8 meters per second, it doesn't make a difference whether you do 80% or 20%. So save your money and just mitigate 20% of the homes. But you have to do it in a smart way so that you can actually be at the lower side of these thin lines, right? So it's difficult to say, but the nice thing is that there is a way to do it. The model shows that there's an optimal way to achieve it, but it's definitely community specific. Yeah.
And I realize this also would probably be somewhat consistent by community, but you have a sense of the wind direction in a matter of
Yeah, absolutely. The wind direction matters. So we ran this analysis. That's kind of what I tried to note early, that that we ran this analysis for the specific cases. We just changed the wind speed, but we kept the wind direction the same for this analysis. We're running actually some analysis on the Marshall Fire now to look at the impact on the damage pattern, giving a variation of wind speed and wind direction. We got the wind speed and direction from NOAA, and we found, I mean, I haven't dug very deep, my postdoc is doing this work now, but actually the wind direction is all over the map for the Marshall Fire area. It's not like it would always be as you would see. And so if that's changing, then how would you expect the damage pattern to look like? And it definitely will change. Yeah.
And I guess also about this plot I'm just curious what the baseline scenario is, or the 0% mitigation. Is the 20% mitigation reducing the damage really substantially?
Well, the one that would reduce substantially is the 80%. So if I mitigate 80% of the building, the percent of building damage drops quite a bit, right? If I mitigate only 20%, then I get more buildings to be damaged, right, in my community. So then you ask, why if I mitigate 20%, the percent of building damage is you know, not substantially, building damage is not, the percentage is not a lot higher, right, than these values. Because if you even do 100% mitigation, let's say this blue now is another one here that has 100%, you will never drop the percent of building damage at zero. So it's not one-to-one correlation, because there is always a probability associated with a fire transmitting from one. The mitigation strategies that exist are not a done deal. It's not, this is, if you do it, we're all safe. Absolutely not.
Yeah, I guess my question was more like, what was the percentage of building damage like after fire?
There was 2,200 buildings in that area. And the number of buildings that were damaged, I believe, was 1,110. So roughly half of the buildings were damaged. Yeah. Yes, yeah. So, yep. So this is the Marshall Fire. Roughly, roughly 2,200 buildings total. Yeah, thanks a lot. Thank you very much. Thank you.